quality हमने discuss किया, वैसे groundwater quality is also subjective, depends on catchment area from which your groundwater aquifer, groundwater जो soil का जो underground जो strata water को perpetually hold करता है, that is known as aquifer. And aquifer has like super saturated with water and all, and water when moves through soil pores and joins this aquifer, which is a geological formation, it comes into contact with soil minerals, rock minerals, in that area, and it will dissolve it. So water dissolves solids. Water will have suspended solids, little suspended solid. It has a lot of dissolved solids. So lot of constituents like iron, manganese, fluoride, arsenic, nitrate, etc., may be dissolved. And water may have a lot of calcium and magnesium causing hardness if water is flowing through what is known as limestone formation. So Chhattisgarh, particularly in Chhattisgarh plains, we are having a lot of limestone formation. So Chhattisgarh plains, we are having a lot of water which is having hardness. A lot of groundwater sources typically have hardness in our area. So for surface water, we have seen treatment schematic. For groundwater also, the treatment schematic is, you can say, normally you go for aeration, you raise the pH by adding lime, go for aeration to remove iron and manganese removal. Then you go for removal of calcium magnesium by water softening so that hardness is reduced, and then you go for disinfection using chlorine mostly. So this is a typical treatment scheme for groundwater. This is another treatment scheme. We won't be going into it. So typically you have unit operation which will involve screen. Purpose of providing screen at the intake structure from where you are collecting raw water from surface water or from groundwater. Groundwater usually you don't require screen because no solids are present in groundwater. It is already filtered through the soil pores. So you provide screen to remove large size solids which can damage pumps, which can choke pipe, which can damage or choke valves. So typical bar screens, these are bars with opening like 10 centimeter, 20 centimeter, 25 centimeter, depending upon the kind of solids you are expecting in your raw water source. You provide a screen, flow passes, raw water passes through that screen, and all the large size. Kindly just mute your mic. Thank you. So raw water is coming through this channel, and it's taken to the intake well through this screen. So all the solids will retain on this screen. Another diagram of screen is this vertical. This is vertical screen, and another diagram of screen is here. So purpose is to protect various equipment, various pipes, etc., which we have downwards. These are some more diagrams of screens, and this is inclined screen. This is screen fitted, cylindrical screen fitted on the pipe itself, pipe which is fixed on the bed of lake or bed of reservoir to collect water, and you have a screen, so no large size solid can pass. A screen can be manually cleaned or mechanically cleaned. So if you are handling large volume of wastewater, raw water, then you need to provide mechanically cleaned screen. Mechanically cleaned screen will have a scraper blade continuously moving through a motor, and this blade will remove whatever solids are deposited. This blade will remove here, and it will drop all these solids on this hand cart, and from this hand cart these solids are taken for further disposal. So usually these solids which are collected in the hand cart are given to solid waste managers for solid waste management. Next, after screening, the next treatment which is usually given is aeration, and purpose of aeration is to improve the dissolved oxygen concentration in water, and secondly to expel out various gases which may be present because of contamination of raw water, and these gases may be because of biological decomposition of organic matter, raw water, and usually whether you are going for aerobic decomposition that is in place of presence of oxygen, or you are going for anaerobic decomposition which is in absence of oxygen. The end product are some gases like carbon dioxide is very common in aerobic decomposition. H2S and methane are common in anaerobic decomposition. So these gas, H2S particularly, will impart very undesirable taste to water. So you don't want that. So you aerate the water so that these dissolved gases are expelled. Then you may have some dissolved metal. So iron and manganese can remain dissolved in water only in their reduced state. So you can say, and the moment they are oxidized and come to higher oxidation state like ferric and manganese, then their solubility is very small in water. They come out water precipitate and can be settled by. So aeration is nowadays common treatment operation which is given to water for expulsion of gases and removal of iron and manganese. So it is very useful for groundwater also. It is useful for surface water also. So we won't be going into these details. So basically, basic principle involved is gas exchange. So typically, if you want to aerate your water body, you need to understand what are the factors will be responsible for efficient transfer of air, oxygen from air to water. And for that, you create the required conditions in your design, in your structure. To enhance aeration, particularly water should be, surface area of water should be enhanced. So water should be released in form of a small water drop by fountain, something or a very thin sheet of water, so that maximum exposure is there. Then you need to increase turbulence so that solubilization increases. You have more and more new area coming into contact with air. You need to increase the time of contact, and then if possible you can increase the pressure of air, compressed air you can supply. So type of aerators are basically based on these parameters, these factors which control the gas exchange. In our case, exchange of air. So we have two type of system. One system is water in air, where you release water in contact with air. So you have fountains, etc., cascade, this thing, fountains, etc. Based on this matter, then you release air into water. So any air diffuser system from compressed air will be air in water system. So this type of aerators are used to this thing. So water in air is spray, and a fountain spray, waterfalls, multiple trays, water falling over multiple trays, water falling in a series of steps known as cascade. Then you can physically rotate the water using mechanical aerators. Then of course, air in water will be diffusion aerators, where you introduce small air bubbles using air compressor in the water volume. So spray aerators are there. Typically, you have a fountain, water coming out of very small size opening in a nozzle, and it comes into form, comes out in form of a spray. So you are enhancing the surface area, enhancing the contact time, and this fountain is very efficient process. 70 to 90% expulsion of CO2, 90 to 98% expulsion of H2S. So this is one example of how do we aerate water in air system. So you are having this water jet coming from nozzle and another water jet. Here also nozzles are there and water is coming out from these jets. Then you can have this effect on providing series of waterfalls or series of multiple tray aerators. And this is multiple tray aerators where water is falling through trays from one tray to other tray, then other tray to another tray. And this way, continuously large area of water is being exposed and air transfer is taking place. Then you can have cascade aerators where you build these steps and there is a lot of turbulence. You can fit a lot of turbulent gravel, etc. on this also to give more turbulence, so that more mixing. Then another this thing, cascade aerator arrangement in drinking. So you visit any drinking water treatment plant, you'll find these structures over there. This is again cascade aerators. This is another arrangement. This is a beautiful this thing with different colors and all. The same thing has been made more attractive. This is a schematic that where you have circular trays and it is falling below that, and this type of plan it will look like this. Then you introduce compressed air in very fine air bubbles through diffusers. So you send compressed air through a pipe, through an air compressor, and this pipe has air diffusers, perforated ceramic diffusers. Mostly diffusers are made of ceramic, and they have small perforations on them. And you can, depending on the size of opening on this opening of perforations, you have fine bubble aerators and coarse bubble aerators. So fine bubble aerators typically less than 2 mm dia, coarse bubble aerator more than 2 mm dia will be this thing. Fine bubble, you will be having more head loss, more friction will be there, you need to provide more energy, but air transfer will be very efficient. Coarse bubble aerator, less friction, but air transfer will be not that efficient. So a compromise has to be made between two. Of course, these diffusion aerators, though they have lot of power consumption, lot of operating and maintenance cost, but they result in high energy, high oxygen transfer rate. So depending on how much quantity you need to handle, what is the situation of water at your treatment plant, you go for diffuse aeration. But mostly, normally in India, we don't have this compressed air diffused aeration. We go for either cascade or multiple tray or fountain aerators, because they are simple to operate. Another diagram for diffused air system. So you have an air compressor which is supplying compressed air to this pipe, and this pipe has manifold, has several laterals, and on these laterals you have what is known as diffusers. And from these diffusers, small air bubbles come out and they burst when they rise to the surface, and air exchange takes place. Very efficient in exchange. Then you can have mechanical aerator where you have installed a motor on a pedal, and pedals are there, and you are rotating this whole water volume very violently. Of course, lot of power requirement will be there, so it is not popular in water treatment. It is used in wastewater treatment. Then after aeration, the water is taken for settling, sedimentation. So purpose is clarification of water. Clarification of water can be achieved in two ways. One is that through gravity settling. So water will be having particles which will have a specific gravity higher than water. And given calm conditions, which we call quiescent conditions, this particle will settle. So one way of clarifying water is through settling. Another way of clarifying water may be through floating. So if particles are particularly having bulk density or specific gravity less than water, then it will be difficult to settle them. Then it will be easier to float them on the surface and then scum them off from the surface. We are having particles which are heavier in specific gravity than water, so we go for gravity settling within a reasonable time. So usually settling time which is given is 2 to 3 hours. So purpose is to separate solids from water, because these solids cause a lot of contamination. So either you can go for flotation or you can go for gravity settling. And purpose is to settle out suspended solids within a reasonable time. So basically, if you are settling solids, so your turbidity is removed, and your further treatment down the line, their efficiency, their effectiveness is enhanced. And because of that, usually sedimentation is provided. So purpose of sedimentation is to settle out suspended solids within a reasonable settling time, reasonable detention time. Detention time अगर बहुत बढ़ाएंगे तो उसमें आपको वॉल्यूम रिएक्टर का सेटलर का ज्यादा देना पड़ेगा और कॉस्ट बढ़ जाएगी आपको. और आजकल क्या होता है कि देयर इज अ कंस्ट्रक्शन ऑफ रिस्ट्रिक्शन ऑफ स्पेस आल्सो दैट इज अवेलेबल टू यू फॉर एस्टैब्लिशिंग योर वाटर ट्रीटमेंट प्लांट. सो यू कांट गो फॉर लाइक ना वेरी लॉन्ग settling time. So typical settling time is limited to 2 to 3 hours. So gravity separation, purpose is twofold. First is that you want to have a clarified effluent coming out of the settling tank. Secondly, your settling should also give you highly concentrated solid sludge, which are solids settled at the bottom are known as sludge. So this sludge, higher the concentration of this sludge, better will be, very convenient will be its management. So typically sedimentation we can understand by this thing that a particle is entering the tank, settling tank, then there is a flow, water flow, and water is coming with certain velocity inside this settling tank, and this particle will be acted upon two forces. One is horizontal inertia, flow inertia of the water, and weight of the water. Apart from this, there will be another two forces, drag force acting on the particle upwards, and buoyancy of the water, which will be restricting the downfall of the particle. And based on this, this particle will ultimately achieve which is known as terminal settling velocity or equilibrium settling velocity. And objective is that by the time the flow reaches at the end of the tank, the solid should strike the bottom of the tank. So based on that, there are various factors which are considered in design of sedimentation tank. I won't be going into detail of these factors. So temperature will affect. Colder the temperature, better will be like settling. Higher temperature, less will be the settling. Currents will affect. We need to provide quiescent conditions. So this is a typical schematic diagram for a settling tank. So you allow the water to enter through this opening. Then you see a wall sort of this thing which is having pores in it and openings in it. This is known as perforated baffle walls. So what happens, we want to create as calm conditions, as quiescent condition as possible here. So to break the inertia of incoming water, this baffle is created. There are a lot many arrangements to create this baffle to allow water. So water will be immediately, its velocity will be reduced substantially and it will pass through these openings. And other water will pass through bottom also. And then water will start traveling to this zone. And in this traveling, the particles will have sufficient opportunity to settle to the bottom of this zone. So typically, settling tank will be having inlet zone, which is here, settling zone, and water will be carried out without causing disturbance to inside of the tank. It is known as outlet zone. And then settled solid needs some space, so there is a sludge zone. So inside the settling tank, you have a settling zone, which is separate from inlet zone, sludge zone, and outlet zone. And basically, when we design, we aim that the smallest particles which we are targeting, particle with smallest specificity, settles by the time the flow leaves the tank. So it strikes the sludge zone, and then it is considered to be removed. Then many a times what happens, the water may contain solids which is very small in specific gravity, very small in size, and mostly in colloidal conditions. And again, these colloidal solids are very finely divided, suspended solids are not desirable. And then you can't settle them within 2 to 3 hours in a settling tank. So we require something so that they also settled out, so that we can straight away go for filtration to clean our water. So for this, we add certain chemicals. One way of ensuring that all these colloidal, very finely divided suspended matter can settle will be to improve its size, increase its size, in turn it's increasing. So we can bring these two particles together, and once they are joined together, and this way the multiple particles come into contact with each other and they join together. So this is known as flocculation actually. So how this is achieved? One way of achieving this is to introduce chemicals in water, and these chemicals are known as coagulants. And what do these coagulants do? Basically, they act by neutralizing surface charge on the surface of these particles. This surface charge, because of this surface charge, when these particles come near to each other, they repel each other. So they can't come near to each other. So first we need to break this charge barrier. And this charge barrier is chemically broken by introducing coagulants which have opposite surface charge. So these coagulants are attracted to these particles and they form a sort of bridge. And what this bridge is known as flock. The result of this bridge is flock, and this flock then attaches other particles, and then it overall becomes a heavier particles and settled out. And this is known as coagulation, flocculation in our terminology. So if you like 1 is to power 10 raised to power minus 6 mm, 5 mm, and the settling velocity, if you can calculate using Stokes law, and a very basic law for settling, formula for settling velocity. So you have 0.73 meter per second, and then you have time of settling if you require, and you having 2 meter tank, then typical time of settling will be like 0.6 meter per minute. Then you have the 3 meter, it will require a million year to settle through 3 meters. So if you say that beyond fine sand, it won't be possible to settle particle finer than this, and we need to do something more to settle them out. And that is why plain sedimentation won't suffice, because particles won't be joining together because of surface charge, and you need to do something. So like I was telling you that most of these colloids will have surface charge, because they have very large surface to volume ratio, surface to mass ratio. So they will having surface charge, and this because of this surface charge, they will develop a layer. So this is a colloid, and which is having negative surface charge in its surface, and this negative surface charge will attract water. Is you can say bipolar, so it will attract positive orientation, positive ions with it, and these ions will be very, you can say, tightly hold with this surface charge, and this layer will move jointly. And as you move away from the particles, this less number of plus minus ions and more number of negative ions will come. So this particle will move like this. This is one layer which is very closely attached to it. It is known as external layer. Another layer which is diffused, which is not that closely attached to it. And this particle will have these two layers of charges attached to it, and they will be moving. So when other similar particle with this similar double layer of charges comes in contact with it, they each repel each other, and you have this energy barrier in millivolts which needs to be overcome. And until unless you overcome this energy barrier, they won't settle out. They will continue to repel each other. They won't settle out. And this is done by adding coagulants. And coagulants work in various ways. But overall, they neutralize the surface charge on these particles. So they become charge neutral. They also attach themselves to these particles because of their gelatinous nature. They are at the surface. They are amorphic. So they attach to these particles, create a flock. This flock catches other particles also, and you have a very heavier particle which will settle out very quickly in the settling tank. So adding of coagulant to neutralize the surface charge is known as coagulation or destabilization. Then bringing particles and this flock together is known as flocculation. So coagulation is done by rapid mixing, and flocculation is done by slow mixing the water in the treatment plant. So coagulation is chemical process that involves neutralization of charges, whereas flocculation is a physical process and does not involve neutralization of charges. So we won't be going into theory of coagulation, broad terminology we have discussed. There are other factors which are considered in designing and operating the coagulation, flocculation process in treatment plant. Common coagulants, we all know Fitgri or alum, which we have been using in our houses also. So most common is alum. And alum is used most of the treatment plants. Other sulfate, which is known as alum, and you can also use aluminium chloride. Nowadays, people have polyaluminum chloride (PSC), which is popular. You can also use sodium aluminate, very effective coagulant, but very costly. So normally, it's also used, but iron salts may impart taste and color to water, so it is not used in water treatment. But iron salts are very popular as coagulant in wastewater treatment. And then since addition of any coagulant will release H plus ions, so you require hydrated lime, addition of hydrated lime to neutralize H plus ion which are generated. So you need to add hydrated lime or magnesium carbonate to help the coagulation process. So how much coagulant needs to be added is done through a jar test, where we take a series of jars in which we have our water sample. This is typical 1 liter cylinders, and these are stirrers. These are stirrers having paddles, and these are rotated by this motor installed on the top this thing. We have a blank where original water sample is there. This is water sample in which we add different coagulant doses, and then we still initially rapidly mix the coagulant into it, then slow mix it for say half an hour, and then see which results in best settling by measuring turbidity, this thing, and that way we determine optimum coagulant dose which is to be added to water for treatment. So coagulation, flocculation is typically carried out in this structure which is known as clarifier. So here your water is coming from aeration, and then water is taken to this flash mixture, where you mix the water very violently, and chemical alum is coming from these pipes, small pipes, added to this tank, and this content is rotating very violently using some rotation mechanism, and this flash mixing are very rapid mixing for say half a minute, 30 seconds or something like that. It is done, then it is released to central column through this underground pipe. It will come through this underground pipe which is not as visible, and it is released to the central column, and from here it is released. So the velocity, this cover is there to reduce the velocity of incoming flow. And in this column, you have this paddle, this stirrer. Very slow mixing of this water will be there for flocculation. Here what we are doing is coagulation, and here slow mixing, rapid mixing is coagulation, so that coagulant chemical is uniformly distributed, mixed this thing, and particles are destabilized. And then it is brought here in central this thing chamber, and here it will be mixed slowly. So it is flocculation, and after flocculation, flock generation is complete. It is taken to the outer chamber where it will settle out. And then this outer periphery, there is weir installed from where it will be taken out in the channel and taken out for filtration, further treatment. So this is typical, another example of clarifier. You are seeing that lot of this thing, white flock is there. This is flocculation is taking place. Lot of white flock is there, heavier flock is there, and this comes from bottom of this chamber and rises above. It helps in settling of particles, and at the periphery you are having outlet weir, which will be collecting these particles. These weirs are there, and it will be collecting these particles and will be taking surface on surface, and they will taking these particles to channel, and this channel will collect and take it to the further treatment, which is usually filtration. So this is a schematic diagram of a small clarifier. So you have pipe coming in here, and water, coagulated water discharge over here. Then this is flocculator and settler, and this there is a peripheral weir which will collecting this and taking it through the channel, effluent channel, to for further treatment. So this is typically RCC tank. Then you have steel structures supported on this RCC tank. This is outlet device, which was not clear in that photograph. So this is, you can say, flocculation and settling chamber. From flocculation and settling chamber, from bottom of this baffle, the clear water will come into this effluent launder. And from this, there is a weir, you can say. This is a weir, and it is having notches, V notches. And from this, water will fall into this effluent launder, effluent channel. And from this channel, it will be collected through the periphery of the tank, and it's taken out for further treatment. Then further treatment is filtration, because even if you have settled it, this water will be having some flock always, and so it is better to go for filtration to remove all these flocks, colloidal matter, and some of the dissolved matter also. So typically you go for coagulation, flocculation, settling, and coagulation, flocculation, and settling. Basically, we are doing in a single tank, and then we go for filtration. So filtration is basically a process in which we retain the particles in the pores of a granular media. That is this common granular media is sand. Usually we have granular sand. We pass the water through this granular sand, and sand pores retain this water, all these particles present in water, and as the water moves through this sand media, through pores of sand media, which are zigzag, in alignment, then a lot of impurities are retained. And not only physical staining is there. Physical staining actually done very small work. Large removal is because of physical adsorption. Very fine particles, which are otherwise won't be removed by any process, are removed by physically adsorbing to the sand particles. So this is so usually most common treatment media is filter media is sand media, and that is why it is known as sand filtration. And sand filtration is a wonderful treatment step. Actually, it removes practically lot of impurities. It removes silts and clays. It removes color, particularly color which is because of suspended solids, which is known as apparent color, will be removed. It will remove all the flocks from coagulation process, and insoluble substances formed from other treatment processes, like you are going for softening, you are going for iron removal, all the precipitation, all the flocks which are formed, like Giardia lamblia is a protozoa which is resistant to chlorine. So if you are not having chlorine and directly not having filtration and supplying water directly to population, that population will have a disease which is known as giardiasis, which is again diarrhea, watery discharge. And then you have Cryptosporidium, again a protozoal which forms spores, protective layer, and is not affected by disinfection. So filtration actually removes them 100%. So nowadays filtration, particularly for surface water treatment, is a compulsory step. And any other particle of nature will also be retained by this sand media. So there can be different type of filter, different classification of filters are available based on direction of flow. So you can have a flow filter when water is coming from the bottom of the filter and coming out at the top. Effluent is coming out, treated effluent is coming at the top. Biflow, from where you are introducing water from the surface as well as from the bottom as well as from the top surface. Downflow, from when water is moving through gravity in the downward direction, that is downflow gravity flow filter. Radial flow, when water is coming in radial direction, and horizontal, when water is coming in horizontal direction. So based on direction of flow of water, you can have different classification of filter. Then based on arrangement of filter media also, you can have sand filter, which is single media. If you are having only sand in your filter, it will be sand filter. You can have dual media, so you can have sand and anthracite coal also. Coal is an excellent filtration media. It also has some absorption, greater absorption than sand also. Then when you are going from more than two media, filtration media, then you can have multimedia filter. Usually multimedia filters are tri-media. Three medias are there. Media are there. One is anthracite coal, another is sand, and another is garnet sand. And garnet sand or ilmenite or GSE, granular activated carbon. It can be used. Garnet sand and ilmenite typically have very large specific gravity. So the advantage of multimedia or dual media filter is that you can play with specific gravity and particle size. So if you operate, design it well, then what happens when you are carrying out filtration, after some time your filtration bed is choked with filtered particles retained in soil pores, sand pores. So water won't flow through, head loss will be too much. So then you need to clean the filter, and the cleaning of this filter is done by forcing water through backwash. So water is, if downward flow filter is there, which is a common filtration water flow direction in common filters, downflow water is coming through gravity and flowing downwards. So to recharge this filter media, to clean this filter media, we need to send water from bottom to up. So upflow direction water will be sent, and with a lot of force, so that all these filter media particles are dislodged completely, and they float in water. And a lot of compressed air is sent, so that rubbing of this media is there with air bubbles, and all the attached impurities from this filter media is released, and it is taken out of the tank, and filter media is clean. So when we do backwash, and again then we take water, backwash water from the media, and then we allow the water to flow, pass through that clean bed, what will happen? The solids will settle based on their size and specific gravity. So if single media is there, then larger size particle will be having more weight, and they will settle at the bottom quickly, and finer size solids will be settled at the top. The problem will be that finer size particle will also have fine pores, and then your filter will choke more frequently. To avoid that, you can play with dual media. Anthracite has lesser specific gravity than sand. Then you can have finer size sand and larger size anthracite coal. So the backwash, they settle, pore side particles settle above, and finer size particles settle bottom, and your filter run time is increased. So most common filter which is used for water treatment is downflow sand gravity filtration under weight of water column above the filter bed. So conventional filtration is known as polishing treatment, जहाँ पे आप you go for aeration, coagulation, flocculation, sedimentation, and filtration. So this is conventional filtration. Sometimes filtration can be used as a one-step treatment, particularly in case of groundwater. You are having water which is not having a lot of solids. So you straightway go for filtration, which is known as direct filtration. So you do filtration and disinfection and supply. Sometimes your water may be very contaminated. It is having a lot of solids, particularly in case of surface stream nowadays. So what we do, we provide a filter which is have large pores, media size, having larger pores, and this slightly remove the suspended solids. It is known as roughing filter. So based on your requirement, based on your raw water quality, based on particle characteristic present in water, you go for selection of different type of filtration. This thing. So filtration is very important. If you are operating your filter well, you get rid of lot of impurities, and you generate very good quality water. So filter, depending on the how much water volume per hour you are treating, filters can be slow rate based on the amount of volume of water which you are treating per hour, or can be rapid rate filter. So you have slow sand filters and rapid sand filters. So slow sand filter are good for very small size water treatment plants, maybe 1 mld or so, and rapid sand filters are good for large quality water treatment plants. Slow sand filter rate is slow, so you require more number of units, large area for the unit to operate. But slow sand filtration, actually, advantage of slow sand filtration is that if you are going for slow sand filtration, you don't have to go for any other treatment. Slow sand filtration directly, and then you can go for disinfection and supply the water. While if you are going for rapid site filtration, advantage is that you are treating lot of water in the process, but you need to other arrangement like rapid sand filter. You can't operate without coagulation and flocculation. So you need whole paraphernalia pre-treatment when you are going for rapid sand filter. Advantage is that you treat lot of water in very small space because your filtration rate is very high. And how this rate is controlled? In slow sand filter you have finer size filter media. In rapid sand filter you have coarser size filter media. So pore size is different, and this is reflected by, you can say, particle size analysis which is carried out in laboratory. And we have certain parameters like effective size, then uniformity coefficient, then coefficient of curvature. Based on that we have understanding that these will be coarser media and this is finer media, and based on that selection is done. So typically after some time in this in slow sand filtration, you get a dirty layer on the surface of this tank, and this dirty layer has lot of biological activity, and typically when this dirty layer develops very thick, then you go for cleaning of this filter. So slow sand filter actually very easy to operate. There is no backwashing involved. You directly apply without any treatment. You apply the water to filter. Filter is having fine sand size, so rate of flow is very small. So rate of retention of smaller size particles is also large. And after some time you have a film developing on this filter bed which is known as dirty layer, dirty skin. Iska actually Slovakian name is Shumutzeke. Polish name is Sumutzeke. Sumutzeke means dirty skin. So this skin has lot of organic matter, lot of microorganisms will develop on it, lot of biological activity will start. And then the head loss will be too much and water won't flow. And, so you at pre-decided head loss, you need to scrap this layer away, and so that filter bed is again renewed. And then, so this is how this slow sand filter is cleaned. This is, you can say, Sumutzeke or dirty layer, which is cleaned manually using this thing, the scrapers, handheld scrapers, and this is collected and stored for cleaning, and then again it is refilled, this thing. So this every, you can say, couple of months or 1 month, you need to clean this filter surface, and every cleaning you will be removing, say, 2 centimeter, 1 centimeter, 2 centimeter layer of this thing. So you continue to remove till you reach you again need to replenish the sand bed using this cleaned and stored sand which you have washed, and then again you apply this sand. So this is how filter is regenerative. This is the schematic diagram how it is operated. So this water, any scum, any undesirable flows out of this thing, any floating solids, and water will pass through this filter bed, collected through this bottom drains, and then taken to this thing, clear water reservoir. This is how. And after this Sumutzeke dirty layer has developed, you need to clean the surface and then start the operation. After it has filter sand has depleted to a larger depth, then you need to filter the clean sand again. And so typically it is when we started water treatment, we started with actually slow sand filters because these are very simple to operate, and particularly for rural water supplies where you need to treat a small amount of water, you can go for very effectively for this slow sand filter. And now since slow sand filter rate of filtration is very slow, you require large area, large volume, also not good for urban areas, large population where you have to treat hundreds of millions of liters of water per day. So you need to go for what is known as rapid sand filter. Rapid sand filter will typically has larger size sand particles, will have larger pores, so flow is rapid. So rate of flow is, treatment is rapid. So that is why rapid sand filter. Advantage of rapid sand filter, of course, it is good for this thing, quick treatment, and you can treat large volume of water, and it is effective for, very effective for removal of turbidity, removal of flocks, and removal of iron and manganese. But it is not that good for removal of odor and taste, bacteria and organic matter, while slow sand filter is very effective in removing that. and it is not at all effective for virus, fluoride, arsenic, salts, or majority of chemicals which are in dissolved this stage. So you need to go for disinfection actually compulsorily after rapids. And rapids and treatment you can't operate without coagulation, flocculation. So, of course, as I was talking about, small lead is required, very effective in removing turbidity, large particles, particularly after coagulation and flocculation. And cleaning time only, you can say half an hour, 15 minutes, 20 minutes, you can clean it. And again, you can put filter back to operation. While in slow sand, you will require at least a day of cleaning to the surface. Disadvantage is it is not effective in removing lot many impurities. And since it is a process is complicated, you require a lot of high investment because backflow, you require a lot of power arrangements and all high operation costs are there. And quick slow sand filter, cleaning time is large. 30 days to 60 days like that. Here you need to clean practically between 24 to 72 hours, depending upon your raw water quality of water. Skilled supervision is required. You want high energy consuming treatment of backwashed water and sludge which is collected, you need to treat that. And this is a schematic for slow sand filter. So basically, influent comes from here. It is applied and it moves into, it form of gravity. It moves to the sand media. A gravel media is there to support the sand media, and then you have under drainage system to collect the treated water and take it out for further treatment. You have the arrangement for cleaning which is known as backwash. So backwash, you have a tank in which this backwash water is stored. And this is only treated water from this rapid sand filter is stored as backwash water in this tank. And when backwashing is done, then this backwash water is introduced from the bottom of the under drain under lot of force. And force is sufficient to raise this sand bed above. And a compressed air is also passed typically. And this sand media just floats in water and rubs against air molecules, gets cleaned, and you take dirty water outside here from this valve opening. This valve, you take the dirty water out, and after the water coming out is clean enough, then you can allow this water to pass out, and then sand settles down, and it's a clean bed available, and you can start again your normal filter operation. This is you can say cross section through the rapid sand filter. So you have under drainage system to collect the clean water. You have gravel bed to support the sand media, and then you have the sand media, and top you have this wash troughs which carry the dirty wash water away from the tank, and which also introduce influent water on the surface media. And this is a filter tank body which is made of masonry or RCC mostly. So this is another construction drawing. I won't be going again. Units are housed in a closed building. So this is typically any treatment plant you visit. Mostly you have a building, a large size building. Will be visible to you next to this thing clarifiers where coagulation, flocculation, settling is taking place. In vicinity of clarifier, you will be having this filtration chambers. And this is a closed building where you have these openings from which you can observe this filtration arrangement. And these are wastewater troughs. These are nozzles to spray water coming from coagulation, flocculation. And this is a sand bed. And these nozzles sprays the water on the sand bed. Water percolates down. Treated water is taken from the bottom of this drain through filter through under drainage system and taken for disinfection. These are some you can say operating data. So this is arrangement again, schematic arrangement to understand how it is operated. So this is a typical diagram. This is from treatment plant at Raipur. They have these rectangular filter beds, and these are filter beds are there. Then you have these channels in which you will be carrying out dirty water. So this arrangement is there. These are sensors which will be measuring the turbidity, and this thing online sensors are there. So this is typically, you can say, this is backflow cleaning is taking place. So you are agitating the filter bed, and this water is coming into these channels, if you can say, and dirty water is taken out. This is another diagram for backflow operation. So you have agitated the whole filter bed, media is separate, and this impurity being light in weight is coming away in this backflow and taken to the surface troughs. This is a filter in operation when treatment operation is there. So you are adding this raw water to this filter bed, and filter water is percolating down and getting cleaned. This is another arrangement for this thing. This is another photograph. So this is, you can say, to take away all the backflow water. This thing are either allow influent water, raw water for treatment. So this is this is typically backflow situation. Actually, water is coming out from troughs and taken through this channel out for this thing. Another diagram for backflow operation. So after filtration is complete, then we take the water, practically all the solids which are in colloidal state, which are in suspended state, and some dissolved solids also, because our adsorption is taking place, they are also removed. So water is completely free from solids, particularly suspended and colloidal solids. And last treatment which is given is disinfection. And disinfection, actually, we don't intend to kill all the microorganisms. Basically, purpose of disinfection is to inactivate the microorganisms which cause disease. And so disinfection is quite different from sterilization. In sterilization, you carry out complete killing of all the microorganisms. While in disinfection, you only inactivate the microorganisms that are pathogenic, that are disease causing in nature. So you target that in disinfection. So disinfection, why disinfection is needed? Because even after all this treatment, aeration, coagulation, flocculation, and settling and filtration, their bacteria can easily pass out. Viruses can easily pass out from this all these treatment, and so we require disinfection of these pathogenic microorganisms, which are very small size, and they may cause disease to population if we supply water through disinfection. Rather, nowadays it is mandatory. You may be getting water from whatever source. It is mandatory to disinfect the water, and disinfection is a compulsory treatment given to all type of water supplied to community. So disinfection history is pretty old, actually. Early 20th century we started disinfection, and there has been dramatic impact of actually that time 1908 or something. We started with chlorination, public water supply chlorination. Cases of rate of typhoid fever per lakh of population. Typhoid is typically because of presence of bacteria, paratyphoid, typhoid bacteria, and they cause this typhoid fever, which is very common in India, even for water supplies. So you can say that 1908 it was introduced, and by 1940, as it became common across various cities in water treatment, practically rate of typhoid is brought to negligible. This thing. So that is the dramatic impact of disinfection, basically. And so if you look at bacteriological quality requirement, you should not have any total coliform or fecal coliform or thermotolerant coliform bacteria or Escherichia coli bacteria in your water sample. You collect 100 ml water sample, your water sample should be free from these bacteria. And to ensure this condition, we need to go for disinfection. So disinfection, what type of disinfectant to select requires a lot of requirements are there. Basically, it should be effective, it should be cheap, it should be easily applicable, it should not be harmful to the consuming population, it should not be toxic in itself. So a lot of requirements are there. And based on different disinfectants. So common disinfectant can be classified in two ways. One which whose action is because of chemical reactions. So common chemical disinfectants are chlorine and its various compounds. So you have chlorine dioxide, liquid chlorine, and you have chlorine gaseous state and all. Then you have sodium hypochlorite, calcium hypochlorite, chlorine dioxide, chloramines also. Then you can have a hydrogen peroxide, you can have copper and silver ionization, you can have bromine instead of chlorine, you can have iodine instead of chlorine. Ozone is very effective disinfectant. Potassium permanganate has been used since long to treat our dug wells, subsurface water treatment, potassium permanganate there. So all these chemical disinfectants have some advantages, some have some disadvantage. Based on requirement, they are selected. Most common in India is chlorination. There are also physical disinfectant. So you have ultraviolet light expo. If you expose thin sheet of water to ultraviolet light, all the microorganisms, pathogenic microorganisms will be inactivated. Then you can apply a electron beam for disinfection. You can have gamma ray radiation for disinfection. You can have ultrasound waves passing through water to break the bacterial cell, microorganism cell, go for sonification, and then you can simply boil the water and carry out the disinfection. So all these treatments have their respective limitations, this thing, and they all these work in different ways. So one is the direct oxidation of the cell wall, direct damaging of the cell wall, be it ultraviolet radiation, be it chemical disinfection. Mostly it is damage to the cell wall, or this disinfectant can alter the cell permeability, and the cell material will leak out. They can enter the cell and alter the protoplasm. So all the biological activity of the cell, compromised cell can't survive, and then inhibition of enzymatic activities. So these are some ways to how the pollutants disinfectant work. Same explanation of same only. So in typical treatment plant, the chlorine, liquid chlorine, chlorine gas converted from liquid chlorine is the choice of treatment actually in modern treatment plant in India also. So you have a chlorine cylinders like this. These cylinders are there, and there is a wall, and there is a separate chamber. And from this cylinder, this thing, and this chlorine is applied through these pipes, and the dosing system is underground. And this is a schematic diagram, give you better idea. So you are measuring the flow through a rotameter, which controls the water flow into this, and this is the water coming to this. You apply chlorine through a nozzle on this, inject the chlorine in this, and water chlorine gets dissolved, and chlorinated water is taken to a tank to give sufficient contact time. Typically half an hour contact time is required. And then this chlorine then during this contact time disinfects the water completely, and water is safe for drinking. Then you take the water to treatment storage, and then go supply it to municipal distribution system. So typically, if you look at to have a recap, you have a water source. You take the water after screening it, and if water is very contaminated, you go for pre-chlorination. You add a small chlorine. You can also go for aeration also. Then you go for coagulation, flocculation, and then you can go for settling, clarification. Then after clarification, you go for filtration, sand filtration, rapid sand filtration mostly, and then you again disinfect the water and take the treated water to the treatment. So this whole paraphernalia is there for treatment. So you have environmental infrastructure to collect and deliver raw water to your treatment plant. Then you have a water treatment plant. Then you have water distribution network of pipes, mains, sub-mains, house connection and all distributed over your city or township. So this huge environmental infrastructure is required to deliver drinking water quality water to our taps. So this much effort is required. But there is again a question that whether water treatment is enough. That we collect from raw water and we treat that water in supply to population. It's not enough actually. The answer is no. We can't do only with water treatment. Why? Because mostly we are getting water from sources which are collected from some area, and whether it is groundwater or whether it is surface water, whether it is flowing stream or it is lake or reservoir or it's underground water. Water will come basically from precipitation. And if you look at hydrologic water cycle, water comes to earth in the form of precipitation. This precipitation, when it moves along the surface of the earth, it is known as surface runoff. And this surface runoff joins the river and lakes or reservoirs. So when you are, what we are doing, because as I was discussing with Dr. Sanjay Singhai also, you might have overheard that discussion, that we are introducing lot of contaminants because of our poor lifestyle, consumerism has resulted in generation of lot of solid waste and lot of liquid waste also. So our waste characteristics are changing both in terms of quantity as well as quality. And because of this, the whole catchment area from where we are getting our water, be it surface water source, be it our groundwater source, the quality of that catchment area is highly compromised. And all the water coming into our water sources highly contaminated, and this contamination is increasing both in terms of quality as well as on characteristics quality also. So we can't depend on water treatment. Nowadays we are having lot of pollutants which are known as persistent organic pollutants. That pollutants once released in nature will remain there for hundreds of years. There is no going away of these pollutants. Nature don't know, doesn't know how to handle them because they are not natural. They are synthetic chemicals. So most of organic synthetic chemicals, there is WHO, this Environmental Protection Agency, United States of America, have a list of these priority organic pollutants. And why these organic pollutants are in priority? Because they are toxic, they are mutagenic, they are they can change our DNA. They are toxic, they are causing cancer, they are teratogenic, they can damage embryo in the mother. So very dangerous. And impact of some of these chemicals will be recognized only after 3-4 generations actually, because DNA change, etc., mutation, etc., it's slow to occur. So we don't know what we are being exposed to, and that it is very alarming situation actually. So we have to move from, we can't rely on water treatment. No technology is sufficient, and even if technology is available for water treatment, it's very costly. Majority of countries in world can't, even developed countries can't afford that technology now. Not every person, all segments of society can't afford. Only very rich people can afford these technologies. So everyone lives downstream actually. And like in your city, from river you are getting water, but there is another city on upstream of river, and there is another city on the upstream of that river, and there is another city on the upstream of that river, and all these cities, all these peoples are disposing their solid waste, disposing their liquid waste, and ultimately this waste will flow to the lowest contour, and lowest level is water body, because water is always available at lower levels. So all these contaminants are joining your water sources, and that is why water treatment, as both from the point of view of technology feasibility and from the point of view of economical feasibility, is not sufficient. We need to move away from water treatment to water management. And we need to protect sources of water, be it surface water source, groundwater source. All this water comes from a catchment area in which falling rainwater, falling precipitation is stored, and it flows and joins surface water, it percolates down and joins groundwater. And there are various sources of contaminant which are contaminating this catchment area. Certain sources which emerge from the pipe, so end of pipe sources or point sources, we can identify those sources very easily. We can tap those sources, like industrial wastewater will be coming out of a pipe. Domestic wastewater also is, if managed properly, it will be coming out of pipe. So these are end of pipe sources or point sources. But there are other sources which are non-point sources, which don't end from a point at a pipe. They are distributed over the area. Like once these pollutants are released, then catchment area will be source. And if agricultural practices are going on, you have agricultural practices contributing to a lot of nitrogen, lot of phosphorus, lot of pesticides. If industrial solid waste, liquid waste is not handled carefully, it will join the catchment. So this will become then area source, and it's very difficult to control area source, pollution in area source. So we have to control at the source. We have to control at the source where the pollution is emerging. So you have this typical challenge to urban water cycle actually. So you have this urban, how do we get water in our cities? So we have rainwater, one source. Fortunately, we have recognized rainwater as a very valuable surface water source. And now we are making attempts for rainwater harvesting, so that we can collect and use that rainwater. And I request you very humbly that as a concerned person, as a concerned citizen who are bothered about future of health of your children and their children, you should install rainwater harvesting system. You should catch the rain where it falls and use it as much as possible. Because this is, even today, it is the purest source of water. So if you catch rainwater and with very little treatment, you can directly use this rainwater. Then you have surface water source and groundwater source. So these three can be our source of water to our cities. Now this source you take from raw water, take raw water and go for water treatment like we have discussed. Then after you have treated water, you go for water distribution. And water distribution, we all use that water which is supplied to you. And remember, mind it, it is all drinking water, quality water. So same quality water we will be using for washing our clothes. Same quality water we will be wasting in washing our car. Same drinking water, quality water in which we have invested a lot of money in water treatment. We will be irrigating our plants, we will be cleaning our floors, and then all this use of water will be generating what is known as flushing our toilet also. And you'll be surprised to know that largest amount of water per day is consumed in Indian household in flushing of toilets. And per person 45 liter. 30 to 45 liter of water is used in flushing purpose. And what is this water? Lot of money has been spent in treating this water to drinking water level. So you may be thinking about whether we can segregate the water use line into houses and then treat water only to drinking water, quality water, which is required for cooking and drinking. Other water can be of slightly little better quality and we can use for other purpose. That is actually future. That is what future is going to be. Then we use it and then we generate what is known as wastewater. This water is wastewater because it can't be used for the same purpose again. So, and then again we are mixing the water, wastewater originating from where toilets and all, where our human excreta is mixed with water. It is very objectionable. But other water which is coming from kitchen, coming from wash basins, coming from washing activities, coming from washing for clothes, which does not have human excreta into it, is known as grey water. Wastewater having human excreta in it is known as black water. So what we are doing today is mixing both grey water and wastewater. And actually grey water is not that difficult to treat. Actually, it can be treated as a level or small, while black water requires actually expert treatment. So we mix all the water, wastewater coming out, and then we need to go for wastewater treatment. Why? Because everybody lives downstream, your water which is coming, raw water which is coming, is not able to handle it. And when population was very small, it was scattered. People used to live in villages, small villages at a distance from each other. Then it was there was a famous quote that solution to pollution is dilution. So पहले ये treatment वगैरह कुछ नहीं था, आप सीधा use करते थे और you used to dispose it into nearby water body. But because population size was less, our lifestyle was simple, wastewater was simple, so it was taken care of natural self-purification process. But now self-purification process, natural cleansing process of all our water body is overrun. It has surpassed their capacity. So you need to treat. You can't discharge wastewater legally also. If you discharge it, legal action can be taken against you. So you need to treat. So further, you are investing in wastewater treatment. And this wastewater treatment or without treatment, it is joint water sources contaminating your water source. So there is a cycle. And this cycle, if you can see carefully, it is non-sustainable. And that is what we are facing in terms of wastewater management and water management. We have entered into a non-sustainable cycle, which is because of our way of life, the way we live, the way we see environment, the way environment is the last priority. Actually, we talk a lot about environment, no doubt about it. Every kid is taught about environment. Every newspaper, every media channel will report about environment. Every administrator, every politician talks about environment. There is talk, but believe me, nobody gives a damn. And as I was discussing with Singhai sir, that if you don't stop giving a damn and start prioritizing environment, future generation is going to have very difficult times. So this is another diagram showing, photograph showing, schematic diagram showing relationship in urban cycles. So this is what you are happening. You are taking the water, using it, various purposes, area source, point source. This pipeline is point source, end point, and this all from surface sources and pipe sources, point source, non-point source are coming back to your water source. So you are treating for and clean water. Again, you are dirting this water and again treating it and again same. And this is being done by every city. So imagine a river which is flowing through various cities. Natural landscape, there is lot of possibility for rejuvenation, this thing. So natural landscape, typically you have this thing, infiltration, lot of infiltration is there, lot of this thing. So you have lot of groundwater flow. So infiltration is 50%. In urban landscape, typically we have stopped infiltration. 15%, because we have covered all the surface from where water used to infiltrate and percolate and join the groundwater. So our groundwater sources are also depleting, and all this catchment area is contaminated. So our groundwater sources are also contaminated. So what is happening? Every city is taking water, dumping waste, taking water, dumping waste. So as you move downstream, water quality deteriorates. And this is a very famous quotation for William Luckell Shaw's. Basically, he was chairman of United States Environmental Protection Agency, and he said that this present way of treating and doing away wood work, you need to go for. So this is, you can say, first city, it is taking out water. Since it is downstream of another city, it needs to treat, and then again it will be discharging wastewater in it, and you need to have a treatment. Then again another city is there, it is treating it, and then using wastewater is generated, again treatment is there. So this treatment cost is going to increase continuously. The water quality will be continuously going to be bad, because one thing is that our population size is increasing. Second is that our lifestyle is consumeristic. So we are using more and more products, we are discharging more and more chemicals. You use several lifestyle products, several cleaning products, which are very harmful to your health also if ingested, and water quality also. So this is actually non-sustainable. We take typical example of Ganga. Ganga starts from Gomukh, water is quality is good. Of course, nowadays it is also compromised because of air pollution. And a lot of pollutants are settling in this area and contributing to pollution in this pristine quality of water. But as it joins urban population, Rishikesh, Haridwar, water quality is compromised. You don't have class A water. And water quality has been classified by Central Pollution Control Board in different classes. You have class A to class F. So class A is the most pristine water, which you can directly take from river. Chullu mein bharo aur pee lo, aachman kar lo. Nowadays, no water is class A water in India. All the water is class B, where you require sufficient treatment before you drink the water. So come Rishikesh, come Haridwar, then Bitur, Kanpur, Allahabad, Varanasi, Patna, until you dispose it off in Bay of Bengal. Every city is taking water, disposing waste. Taking water, disposing only liquid waste, solid waste also. So we are entering in a zone of actually non-sustainability, as far as technology is concerned, as well as then change. And the climate change is going to change the precipitation pattern, going to change the evaporation pattern, going to give rise to a lot of siltation, a lot of soil erosion. It will be very intense. You have cyclonic events increasing frequency. Last decade, people say that we saw maximum cyclones in remembered human history. So things are going to difficult. So if we don't keep environmental infrastructure priority, management of environment in priority, we are going to face huge challenges. And challenge is that the population in 21st century, we need to provide water is basic requirement. We need to provide reliable water, safe water, and otherwise population won't be able to survive. So we need to tap this urban water cycle. We need to close the water cycle, and we need to collect the rainwater, catch the rainwater. We need to segregate our wastewater, black water separate, grey water separate, supply water according to requirement to even households also. And we need to maintain that, manage that our catchment area is as clean as possible. We don't discharge any liquid waste, solid waste in this catchment area. And we treat all the water, and our water requirement for our city we fulfill from local sources only. Then only we will be able to. We need to manage our solid waste. We need to manage our industrial waste well. We need to stop open defecation completely. We need to install septic tank if at all required. They are sealed, watertight, water sealed, so that there is no leakage. Lot of contamination to groundwater in cities, Indian cities like Raipur, Bilaspur, is because of septic tank, leaking septic tank, which join the subsurface water. And then you install a Tullu pump on your water supply line, and when water supply is stopped at the other end, you suck all the contaminants, and you are having typhoid, you are having jaundice in every family practically. So this is again an idea about water management, managing the water cycle. So you need to tap the rainwater, and that's very important. You need not use the groundwater as far as possible. We need to stop use of groundwater. We need to depend on rainwater, treated wastewater, and treated stormwater for our requirement. Groundwater usage should be immediately stopped. Why? There is a reason. Every year, if you look at the groundwater board report on quality of groundwater in India, every year more and more number of people are being exposed to poorer groundwater quality. Arsenic concentration is increasing in more areas, fluoride concentration is increasing in more areas, iron and manganese concentration is increasing in more areas. And more districts of India are coming into this. Why it is happening? It's not that you are knowingly putting something in your groundwater. It's because of poor management of waste, in overall poor waste management. And second reason is over exploitation of groundwater. What happens? You might remember your chemistry, school chemistry, that there is a principle which is known as Leach-Atelier principle. And in Leach-Atelier principle, basically, if you go, Leach-Atelier principle says that chemical equation will move in that direction in which we are taking out some product or reactant from in that direction. So if I am from chemical reaction, I am taking something from the right side, chemical reaction will immediately start moving from left to right, so that that quantity which has been taken out, the equilibrium is maintained. What is happening in case of groundwater? Groundwater aquifers are created over thousands of years, over lakhs of years of water percolating through soil pores, joining the permeable strata, then passing the permeable strata to join the impermeable strata. And then the strata becomes saturated in thousands of lakhs of years, and then you have groundwater aquifer. And while this process is going on over thousands of years, water has lot of time to come into contact with soil minerals and rock minerals. And depending upon the local catchment area geology and geochemistry, you have water, we have an equilibrium balance in your surface reservoir. Equilibrium balance is there that under the static condition, steady state conditions, the minerals will get dissolved from the rock and soil formation. And once reaches the capacity of water solubility in that condition, in those conditions of temperature, pressure and everything, the mineral will precipitate it out. And there will be dynamic equilibrium where you will have a different concentration of all these minerals in groundwater. Now, what you are doing that, you are then groundwater is reaching the aquifer. So what you are doing, you are disturbing the Leach-Atelier equilibrium. You are taking out water, and with water you are also taking out minerals. So what will happen? Our surrounding rock will start leaching into this groundwater, and concentration of all the minerals will become more. That is why more and more arsenic, more and more, you can say iron, manganese, more and fluoride, and all are toxic to us in higher concentration. And if you don't stop extracting groundwater, you are going to have more and more problems with groundwater consumption. So you need to immediately, wherever possible, you need to stop groundwater. You need to collect rainwater. All the rainwater should be collected. It should be used. All the stormwater should be collected at local level. It should be used. All the wastewater should be collected, properly treated. And based on different possible uses, they should be used locally. And when all our uses have been satisfied, then only we should discharge any wastewater or any stormwater which is treated to the desired standard to maintain pristine quality of rivers, our lakes and reservoirs. Then only we will be able to supply reliable water, safe water, palatable, potable, wholesome water to community. So, and this is actually urbanization, the kind of civilization growth we have taken place during past centuries is actually, we and our next generation will be paying the price for it. And one is that urbanization. Urbanization, typical city size is increasing every year. And globally, it is a global phenomenon. All population in rural areas is decreasing, people migrating to cities because cities are engine of growth. And cities are engine of growth, so they provide a lot of employment opportunities. And civilizations are shifting from agriculture to industrialized society. And that is the concept behind actually development. Unfortunately, development means you consume more resources, you burn more coal, you burn more oil, you generate and consume more electricity, you consume more products, more raw material, more finished product, you generate more waste. That is development, that is urbanization. So in India particularly, if you look at last census data, so fortunately metropolitan cities population practically it is stabilizing. But what we are seeing is that smaller cities, you can say other non-metro cities or class A and class B cities, towns, their population is increasing a lot, at a very rapidly rate. And in particularly this was observed in 2011 census, and 2021 again we are going to have census, new data will come. But 2011 census, it was observed that migration to metropolitan cities is reversing actually. People are forced to move back from metropolitan city, and reason is that the kind of services which are required in metropolitan cities are skill oriented, and a rural person coming without skill in the metropolitan cities won't be able to get job nowadays. So they don't have any job there without being skilled, some sort of skill. So they are coming back to class A and class B cities, where they can have this hard tiller, they can have this manual driven rickshaw and all, or they can work as labor. So because of that, this population shift is there. But super urbanization is going on. And challenge is that if you look at India, actually we have 18% of world's population, and we have 4% of the world's fresh water. So obviously there is a, you can say, friction, there is a challenge. And according to government's report, some 21 cities, this is NITI Aayog report. NITI Aayog has brought down a document. This document is publicly available, status of water in India. And according to NITI Aayog's data, research and projections, by 2020, that we are sitting in that same year, 21 of our major cities will be having water scarcity, water challenge. And you have seen scenario in Chennai previous summer, scenario in Bangalore, scenario in Hyderabad previous summer, scenario in Delhi. There is hue and cry, even in your cities. In Raipur, come March, and we have see this tankers going around in the city, creating a lot of air pollution in the city. So we need to supply them through tankers. So by 2030, 40% of Indians will be without access to good quality fresh drinking water. So that sort of challenge we are facing. And you can't solve it simply by money. India, simply we don't have money because we are having 130 crore population, resources. You need to reduce your consumption. You need to be careful about waste you generate. So be it public policy, be it personal policy, you need to be an waste water management index report released by NITI Aayog in 2018. By 2030, the country's water demand is projected to be twice the available supply, implying severe water scarcity for hundreds of millions of people and eventually 6% loss in the country's GDP. And you can very well imagine what this 6% loss in GDP can do to this country. Employment, huge type, another type of, you can say, pandemic we are looking at. We don't make ourselves aware of these things. WHO says that individual requires minimum 25 liter water daily for meeting his or basic hygiene and food needs. Minimum 25 liter आपको चाहिए. The rest is used for non-potable purposes like mopping and cleaning. अभी हम क्या कर रहे हैं? 135 liter per person per day. Normally जो अभी स्कीम हम डिजाइन करते हैं, we design it 135 liter per person per day. Out of that 135 liter, 25 is actually required for drinking water quality. Rest is all for other uses where you don't require drinking water quality. So why don't have initial investment cost will be more, but why don't have two level of supply so that water treatment cost is reduced? Similarly, we need to channelize our wastewater, grey water, black water. Grey water can be easily treated, can be easily recycled, can be reused safely. Black water you can then have less volume, you spend less on that, and then you can manage that very well. Paradigm shift is needed, and until if you want safe potable water available at our doorstep to our kids, to next generation, then first thing is we need to improve water use efficiency. We need to reduce leakage. Typical Indian city leakage in water supply lines is 30% to 40%. And this is all treated water in which you have made huge investment. Lot of theft is there, lot of leakage is there. Why? And majority of these leakages are, why these are there? Because of rampant corruption. They are because of carelessness, because of poor quality of workmanship. हर आदमी को शॉर्टकट चाहिए, हर आदमी को आसानी से पैसा चाहिए, किसी को अपना काम ठीक से करना नहीं है, तो you are leaking 30% to 40% water, and it is hampering your lifestyle, it is having your quality of health, and it is affecting your quality of life, it is affecting your survival. You don't know कि आपके बच्चे का दिमाग आज तेज क्यों नहीं है ना? Water contaminated, his mother has her mother has ingested, or he or she is ingesting, maybe the reason for that, you never know, and that is the status today. So you need to recharge, restore the local water body. आपने हमेशा water bodies को पूजा की है, आज भी आप कोई बड़ा काम होता है, शादी होती है, पहले सबसे पहले ताल पूजने, कुआं पूजने जाते हो, लेकिन ये क्या हुआ, ये हमारा आ गया किसमें, ढोंगाचार में आ गया। जो उसकी फिलॉसफी थी, जो उसकी स्पिरिट थी, जो उसकी सोल थी, वो हम मिस कर गए। कि पूजने जाना है माने ये शपथ लेते हैं हम कि हम आपकी क्वालिटी की जिम्मेदारी लेता हूं मैं आपको प्योर रखने की, चाहे मेरा कुआं हो, चाहे तालाब हो, चाहे नदी हो, है ना? नदियों को हम मां कहते हैं, और हम करते क्या है ये हमको सबको मालूम है। और इसमें आप कुछ भी चेंज कर लो, आप बोलो मूर्ति विसर्जन नहीं करो, धर्म आपका आड़े आ जाता है। अरे बाबा, उसी को आप पवित्र मान रहे हो, उसी की पूजा कर रहे हो, और उसी को ठीक करने के लिए, तो ये कैसा धर्म है आपका जिसमें आपका विरोधाभास है? ये दिखाता है कि हमने स्पिरिचुअलिटी और सोल जो है वो कहीं हम मिस कर रहे हैं, और हमको जागना पड़ेगा। इट इज टाइम टू गो बैक, है ना? आपको पानी को चार्ज करना पड़ेगा, उसका पैसा जितना लग रहा है उतना लगाना होगा। अभी सब्सिडाइज है पानी, इसलिए वेस्ट भी करते हैं हम लोग सब। It is time to go back and start using our traditional practice of rainwater harvesting. पहले rainwater harvesting आप चले जाओ इंडिया के रूरल एरियाज में, है ना? तालाब है, छत्तीसगढ़ जो प्लेन है ये तालाबों का प्लेन है। हर गांव में दसियों तालाब होते हैं। रायपुर शहर में 154 तालाब थे, 154 ponds, lakes we used to have to collect this rainwater, catching water. Now we are having 45 ponds left in Raipur. 154 से ये पिछले 100 साल में 154 से 45 पॉइंट्स पे आ गए हैं, और आपने सारा सरफेस कवर कर दिया, कंक्रीटाइज कर दिया, आपको बहुत नीट एंड क्लीन चाहिए सारी चीजें, एंड योर ग्राउंड वाटर इज डिप्लीटिंग। प्रेजेंटली इंडिया कैप्चर्स ओनली 8% of annual rainfall. You can visualize the condition that even if you catch 20% of rainfall, your problem, it is water problem is water scarcity, water resources challenge is not challenge of water availability. Water is available plenty even today. Poor water management, unscientific water management is the cause. Annual rainfall will be very interesting also. It's interesting because it's complex, and to address everything you need environmental infrastructure. So after water usage, what you have done? You have diverted wastewater. So you have environmental infrastructure, water treatment, and wastewater treatment plants are there. Lot of this wastewater treatment unit operation processes are similar to water treatment, but some additional are there. You go since biology. Presently, you would be very happy to know that Government of India has made it mandatory for every industry to go for zero liquid discharge, ZLD. Industry can't discharge even 1 milliliter of water into surroundings. They need to collect all the wastewater generated by them. They need to treat that water and reuse that water within their premises. So if you find any industry discharging outside, you just get a photograph, send it to pollution control board is, and share it on social media, WhatsApp and Facebook, so that everybody knows that this industry is polluting, because it's you, your family, your kids, their kids who will be paying price for this. इंडस्ट्री वाले को तो मिलेगा, हालांकि उसको भी कैंसर हो रहा है, ऐसा नहीं कि वो छूटा हुआ है ना, नेचर सबके साथ बराबर डील करती है, बट वी हैव टू बी कॉन्शियस एंड वी नीड टू गो फॉर closed loop system, because nature operates in cycles, nature operates in closed loops. So we have to manage this closed loop, closed cycle in every level of our living. Then you have to go for solid waste management also. Solid waste management again, lot of legislation has come, particularly in 2016. You have actually different type of solid waste. You have different type of rules. You have municipal solid waste management rules. You have plastic waste management rules. You have hazardous waste management rules. You have waste management rules for battery special. Then you have biomedical waste management rule. So all different type of waste. India, we don't have any shortage of legislation, any shortage of rules, any shortage of act. What we lack is our priority given to environment. And until unless we give priority to environment, all our environmental infrastructure will not be sufficient to provide us healthy conditions. So I'll stop here. I think 5 minutes, if Agrawal sir permit me, then we can have 5 minutes for question answer. If you have any queries, any questions.
Yeah, sure.
Yes.
Sure. We can have some interaction.
Some interaction is required. So let's, I'll stop presenting and we can just one-to-one we can interact. हाँ बग्गा साहब क्या पूछ रहे हैं?
Hello.
Yes.
I wish to ask only 2 questions. Is there any method to quantify? Hello, am I audible, sir?
Yes, sir. You are audible. You can ask your question.
Yes, you are audible.
Is there any method to quantify water demand for agriculture, industrial, and other kind of amenities in the town and cities? And my another question is, do we also have some technical manuals for water treatment?
Very important question, Bhagga Saab, and fortunately we do have, you can say, estimation techniques to estimate present day agricultural water demand, to estimate present day industrial water demand, and water demand for other purposes also. There are methodologies, there are estimation methods that are available, and not only this, you can also project future water demand also, based on certain growth factors for industry, growth factors for this thing, and also you take constants also, and these can be projected. There are established methods for that. Second answer is that yes, fortunately we have manuals practically for all type of treatment. Yeah, so Ministry of particularly Urban Affairs, they have an organization which is known as CPHEEO. So, Bhagga Sahab, if you Google CPHEEO, CP Central Public Health Environment Education Organization, CPHEEO, double EO, manuals. You Google it, you will get all the manuals for solid waste management, for for every type of environmental infrastructure, you have manuals laid down for designing, for establishing, constructing, establishing, operating, and maintaining these infrastructure. So, very important question. I am thankful to you because I missed out on this thing. So you raised a very important. So, lot of resources are available. Government of India has published lot of manuals, lot of guidelines are there in Ministry of Urban Development website. Also, you will get CPHEU website. Also, you will get Central Water Commission website. Also, you will get CPCB Central Pollution Control Board website. Also, you will get lot of material. Pollution Control Board, State Pollution Control Board website. Also, you will get lot of